So today we are going to learn about SR flip-flop. SR flip-flop is made from SR latch. Now, what is an SR latch? So an SR latch is basically two NAND gates, uh, but uh, the output from the second is the input for the first, and the in output for of the first is an input of second. So this basically is an SR latch. Okay, now we will draw the truth table for this. Okay, so the truth table is basically when S are like Q and it is Q like inverted. When S is 0, R is 0. So see here, if S is 0 and R is also 0, so if you remember the NAND truth table, it's basically AND with a NOT. Okay, so it's input, output. Okay, so I'll just erase this part. Okay, so A, B, and out. So if A and B both are 0, so 0 and 0 and is 0 and not 1. 0, 1 and is 0, 0, 1. 1, 0, 1, 1, 1. 1, 1 and is 1 and not 0. So this is the truth table for NAND gate. If any of the output is 0, the any of the input is 0, the output tends to be 1. So this is, if we let S is 0, this should be 1 and this is connected to this. So 0, 1. This also gives 1. So it is kind of a contradictory case as the output should be uh, inverse of each other. So this is a contradictory case. Contradictory case. Now let's move to 1 and 0. Now if I let's use another. Now if S is 1, just- now if S is 1 and R is 0, so let's take this. If any of the input is 0, the output should be 1. So this 1 goes into this 1 and 1, 0. So Q is 0 and Q naught is 1. Similarly, if we do 0, 1, 0 and 1, Q will come out to be 1 and Q inverse should be 0. Now let's talk about 1 and 1. If both the cases are 1, so S is also 1, R is also 1. Uh, Now Q, this case is called memory. Okay, I will now be explaining how the when S is equal to 1 and R is equal to 1, it becomes the memory case. So the SR latch basically stores the outputs in the state which they were. So let's take the second case. So S is 1, R is 0, and Q is 0, Q naught is 1. Now when I change both the inputs to 1, so uh, Q is basically 0. So this comes in as 0, and this remains as 1. So as you can see, when S and R both are equal to 1, the outputs remain the same. So before S is equal to 1 and R is equal to 0, uh, Q was equal to 0 and Q naught was equal to 1. But after uh, we put S is equal to 1 and R is equal to 1, now Q is basically the same, 0, and Q naught is basically equal to 1. So it stores the output. You can do the same with third case also, and the first case is contradictory, so we need not doesn't do not need that. Now let's come to uh, SR flip-flop. So SR flip-flop is basically uh, when this is S, this also, this is R, and this is clock. This is clock, and these are connected as, let's take them S star and R star. So I have to redraw this. There's not much space here. So I'll just draw them. Now we can also do this. This means, oh, sorry. It's basically this. It's kind of messy, but it's same as the SR latch. And this is Q, this is Q naught. Now we can make the truth table of SR flip-flop, or SR. So now here it is S. First here it is clock, SCLK, clock, S and R. If the clock is 0, as you can see from the truth table of NAND, if any of the input is 0, we get output as 1. So no need to calculate S, no need to calculate R. We simply get, let's make a column for S star and R star. So clock is 0, S is, you can take anything S, R you can take anything. So it's like 1 0, 1 0. You can take anything. Now S star, if clock with S, so the S star is 1. Similarly, R star is 1. So Q Q naught. This is basically memory. Okay. Now, when the clock is 1, that's where the story begins. S, let's take S as 1. And let's take S as 1 and R as 0. So when S is 1, clock is 1. Okay, both are 1. So according to that, it should be S star should be 0. And when any of the input is 0, it should be 1. So this is the same case when in the SR latch 0 and 1. 0 and 1 gives us 1 and 0. Okay, this is 1 and 0. Now let's take clock remains 1. This is 0, this is 1. So combining these two, we will get S star as 1. And combining this and this, we will get 0. So it is the inverted case 0 and 1. Now let's take clock S1 and we take both of them as 1. So this is 0, 0. Okay, both are 0. Now if we check the truth table, 0 and 0 is the contradictory case. So the next case is when the clock, what just happened? The next case is when the clock is 1 but other two are 0. So 1 and 0 in AND gives us 1. 1 and 0 in AND gives us 1. So this is the 1 1 case. 1 1 case, as you can see, it is the memory. Now, as you can see, our truth table is complete. So you can note it. I also wanted to tell what is a D flip-flop. It's basically a modification of SR flip-flop. As you can see, let SR flip-flop. It is actually denoted as this. Denoted as uh, so it's a rectangle with this S R clock, and these are the outputs. Now D flip-flop is basically when, as you can see the truth table of SR latch, when S and R are opposite, then only it is showing the output as 1 0 or 0 1. So we need only these two cases. So using some tricks, not tricks, it's basic maths, we can just use a NOT gate in using a single input and NOT gate to R and same input to S. So it's like this. This is a NOT. This goes on and Q. So basically we take the same input, but we divide it into like its opposite and throw it at S and R. And the clock is there. And this is an SR flip-flop. So yeah, this is basically what and what a D flip-flop looks like. Okay, thanks.